As the last part of this lecture, we're going to look at an important application of radiation coming from the atoms. It's called laser. We all know about this term laser. Laser, in fact, is an acronym. It stands for light amplification by stimulated emission of radiation, LASER. That's what laser stands for. We know how important laser is today. We use it everywhere. So what's the physics behind laser in a nutshell? We're going to describe it in a brief term. It's actually an entire branch of physics all onto itself. Let's see here. What is the physics behind laser? The physics behind laser, the physical principle, was first illustrated by none other than Albert Einstein. He published an important paper in 1917. It's called The Quantum Theory der Strahlung, German word for the quantum theory of radiation. Here is what the paper says. Okay, suppose there are two energy levels in the same atom. The energy difference is delta E. It's fixed. Now, a photon comes in. If that photon has a frequency that's too high or too low, it doesn't do anything. Okay, the electron won't do anything when it sees that photon. But when HF equals delta E, then something will happen. This photon will see one of these two things happening when it passes by that when it passes by that atom. First possibility, an electron in a lower orbit will then receive this much energy from the photon, and then what happens? It jumps to here, right? Because the energy difference delta E is equal to HF, so it has just enough energy to jump there. So that is called absorption. So as a result, the photon is gone. It's being eaten up by that electron. So one photon in, zero photon out. But there is another possibility, and that's kind of a little weird, but it's true. And that is, if there is already an electron here, this electron, upon seeing that photon, can actually jump down by itself, radiating another photon of the same frequency, because delta E, the energy given up by the electron, equals HF, right? This only happens when that's the case. So now you have one photon coming in. This photon was never actually eaten up by this electron, because this electron doesn't need any photon. It doesn't need to absorb any photon. It actually gives up a photon all by itself. So now you have two photons coming out. This is called stimulated radiation. This radiation by the electron doesn't happen by itself. It is because there is a photon coming in, and the electron is being stimulated by this external photon, so it radiates. It's called stimulated radiation. So in that second case, one photon in, two photons out. Again, first case, one photon in, zero photon out. Now, if these two events happen with a 50-50 chance, then half the time the photon comes in, no photon come out. Half the time it comes in, two photon out. You can easily do the math and find that overall, if you get 1,000 photons in, 1,000 photons will come out. That is boring, okay? You don't gain anything, do you? And what Einstein did in his famous paper was to show, based on known physics back then, using Planck's radiation formula and statistical physics. You can easily read that. We just don't have time to discuss that. He showed that an electron in the upstairs and an electron downstairs, upon seeing that photon, has the same probability of either jumping down if you're already up there, or going up if you're down there. Okay? These are characterized in the so-called Einstein coefficients. The coefficient for this guy to jump up, the coefficient for this guy to jump down. They're equal to each other, according to the Einstein paper. So, if you have equal number of electrons already here and already there, what that means is that since an electron already here is equally likely to go up, like an electron already up there equally likely to go down, then when you get a whole bunch of photons coming in, 50% of the time those photons will cause the electron to jump up, another 50% of the time will cause the photon to go down, and therefore there is no net gain or loss in the number of photons after the photon passed through this atom. But imagine what happens if you have more electrons in the lower energy state less electron in the upper energy state. We're talking about a whole bunch of electrons, okay, a whole bunch of atoms, okay, not a single atom. So don't worry about the Pauli principle because we have many, many, many atoms. Okay, so let's say we have a whole bunch of we have a whole bunch of atoms here, electrons here, but not that many atoms there. That's a normal distribution, right? The lower energy corresponds to greater number of electrons. Then overall, the effect is that more electrons would jump up, less electrons would jump down, because you got more electrons to start with than you have the electrons up there, right? So the net effect then is that as the photons come in, you got less photons coming out. The net effect is that some electrons will make a gain in energy jumping up, eating up part of these photons. We don't want that. We want light amplification. We want less photon in, more photons coming out. How do you do that? So we want this event to outnumber that event. We want more stimulated emission than absorption. And this happens only if you got more electrons in upstairs than electrons downstairs. That way, with the same probability of going up and going down, since you start with more electrons, the net effect is that more electrons will come down than electrons going up. Then you end up with more photons coming out after passing through the medium of atoms. So you see here, to get amplification of light by interacting with the atoms, we have to achieve what's called population inversion. And that is, we must have an abnormal situation where more electrons are found in a higher energy state than electrons in a lower energy state. That seems to violate the statistical distribution, right? You know, statistically, according to the Maxwell-Boltzmann distribution, the lower the energy, the greater the number of particles can be found there. You must violate that in a certain manner to achieve what's called population inversion. More particles here, less particles there. That's how you can achieve, lasing. And to do so, we have to use a procedure called optical pumping. This is a way of pulling particles from low energy state and push it to the upper state. So the upper state will have more particles than lower state. It's called optical pumping. The Einstein paper was published in 1917. And a lot of intermediate steps and discoveries were made, but it was not until 1960 when the first laser, a ruby laser, was actually put into operation. And this was done by a scientist by the name of Mayman, and it was very local. It was first in operation in Malibu, in the Hughes Aircraft Company in Malibu, California, 1960. And it hasn't been that long since then, but the science of laser has now become such an incredible invention. The application is just everywhere. Let's take a closer look at population inversion and pumping, optical pumping. So we have a case where you have achieved population inversion. Okay, here's more particles upstairs, less particles downstairs. Again, these represent many, many, many atoms, not just two atoms, not just one atom. Otherwise, you only have two here and two there at most. Okay, one photon coming in. This photon, as it comes in, it has the same chance of causing a particle going down and another particle going up. But since there are more particles there, the net effect is that you got some particles going down, producing more photons. So that's how you amplify light. Okay, now, in a population inverted system, if you try to apply the Maxwell-Boltzmann distribution, N2 is the number of particles there, N1 is the number of particles here in the lower energy state, then N is proportional to e to the negative energy over kT. Remember, that's the Boltzmann distribution, right? And if you take the ratio of N2 over N1, that is e to the negative delta E over kT. Delta E is a positive number representing the energy difference. But I want N2 to be greater than N1, right? That's population inversion, right? Now, if you solve this, you find that the only way to make it happen is for T to be negative, right? Because e to the negative something, if the whole thing stays negative, it can never be greater than 1, right? No matter what that T is, T can be positive infinity, you still will never get population inversion. If you want to satisfy this equation, T has to be negative. You have what's called negative temperature. That is weird. Not only is negative temperature a weird concept, because we know absolute zero is still zero, it's not negative. The negative temperature is in fact hotter than positive infinity, because even at positive infinity, you have e to the power 0 basically. That's still 1. I want greater than 1. Isn't that even hotter than positive infinity? Look, the higher the temperature, the more particles go up, right? But even at positive infinity temperature, you only have 50% of particle here, 50% particle there, and that's when e to the power, you get e to the power 0, which is 1. But now I have, say, 60 here, 40 there. Isn't that true that this negative temperature is actually hotter than positive infinity? So you wonder, how do I put something that is hotter than positive infinity in temperature in my pocket? Huh? A laser pen. How does that work? Isn't that going to melt everything, destroy everything? Is there something weird about this argument? This can't be true, right? Okay, so here's the thing. Negative temperature is not a real temperature. It is an artificial concept. The mistake we made here is that we're not supposed to be using the Boltzmann distribution. The Boltzmann distribution is achieved upon thermal equilibrium, and that is, you have a system, right? You mix different temperatures together, whatever. You leave it alone. Eventually, it reaches the same temperature. You leave it alone. It's an isolated system. Eventually, it's going to reach Boltzmann distribution, thermal equilibrium. But our system is not in thermal equilibrium because it is never left alone. You must keep more particles upstairs than downstairs. Even as particles jump down due to lasing, you must maintain population inversion by pushing more particles back up, okay, as the particles come down. This requires energy. It's called optical pumping. Optical pumping receives energy, requires energy. So you have to plug the laser into a power supply. That power supports optical pumping. So the laser system is never left alone. It is plugged into a power supply and consumes external power. It is not an isolated system. Therefore, by definition, it is not in thermal equilibrium. You do not have a meaningful temperature to talk about. This is not a real temperature. Okay, a negative temperature is not a real temperature. But it's just, it's just a saying. When we say negative temperature, what we really mean is that population has been inverted, so N2 is greater than N1. That's what it means. So, how do we perform the magic? How do we achieve population inversion by optical pumping? How does optical pumping work? Well, here is an example, the famed HeNe laser, helium-neon laser. It's a gas laser with a mixture of two gases, helium and neon. And only one of these two gases, the neon gas, actually performs lasing. That is, this is the medium in which emits laser light. So what do we need the helium for? The helium is there to provide optical pumping. So here's the thing. You put HeNe gas in a chamber, and you apply a high voltage so that you ionize the atoms, so then they will then accelerate under the influence of the high voltage difference at very high speed. They have a lot of kinetic energy. And this helium has a ground state, and here is the first excited state, which is about 20.61 eV above the ground state. And it then collide with the neon atoms. We're talking about collision. And you have an energy level in helium, which is quite close to an energy level in neon, okay, in one of the energy levels in neon. It's actually a little bit lower, but remember, this guy has a lot of kinetic energy on top of that, okay, easily, so you can easily provide energy difference. So this guy may have enough energy upon collision to pass its energy to helium, or to neon, to neon, okay? And then, so the neon will then reach this energy state. So you got, upon collision, you got a lot of electrons in the neon atom going to here. Okay, because you can pass energy to neon so that the electrons will transit from here to there. So you got a lot of particles here. Once it's here, it will try to go back to the ground state, but it doesn't do that immediately. This is E3. The ground state is E1. Okay, you go from E3 to E2. E3 is what's called a metastable state. What does that mean? It means it is not completely stable, which means the electrons won't sit there forever if there's a vacancy, but it is not as eager to jump down as if it's a normal state. It's a metastable, semi-stable state. It will take a little bit of time going down to here, going down to here. And once it's here, it will take no time, almost no time, to go down to ground state. Okay, this is called a three-stage laser. There are three energy levels. So imagine you have a lot of particles here through optical pumping from the ground state. Okay, a whole bunch of particles. Because of optical pumping, you have actually more particles in this state than that state. Okay, than that state. So that's population inversion between E3 and E2. Now, it takes some time for the photons to come down, but since it's population inversion between E3 and E2, you're going to have lasing. You got more particles. You got photons coming out. That's the laser. The nice thing about it is that once the electron jumps down to here, it wastes almost no time going down to ground state. So that keeps E2, this level, very clean. Okay, it's not going to sit there forever. Otherwise, after some time, you're going to reverse the population inversion. So lasing will stop. Once it's here, it wastes no time going down to ground state. The ground state is quite empty because of the optical pumping going on. So this intermediate stage is of great importance because it's almost nearly clean. You don't want this thing to go down directly to the ground state because once you're in the ground state, you got no place to go any further. You cannot vacate yourself. But you are going down from E2, E3 to E2 in an intermediate state, which is kept mostly empty, mostly clean by jumping down to the ground state. So that's how you maintain a good population inversion all the time. And here's the energy diagram going from E3 to E2, 20.66 eV minus 18.70 eV. The energy difference is emitted in the form of the famous red light, 632.8 nanometers. You can verify for yourself. Delta E equals to 20.66 eV minus 18.70 eV. Okay, and you let that equal to Hc over lambda. Hc is 1240 eV nanometers. You divide this by lambda. This lambda is equal to 632.8 nanometers. So that's how the Heaney laser works, as an example. Of course, to achieve the optical pumping, you have to give the, you have to ionize the helium atoms and accelerate them through electric potential. That takes energy. That energy is what causes the optical pumping to sustain. So there is conservation of energy there. So this is a famous application of the radiation of energy levels between energy levels in the atom, which is laser. Laser has extremely important applications everywhere. Why is laser so incredibly useful? First of all, it's got highly concentrated energy, highly concentrated optical energy, and it's highly collimated, very straight, okay? And it's very coherent. The beam is very coherent, optically pure. It's very, very long wave trains. And we can use this to our advantage under a whole variety of different scenarios. In electronics, for example, all so-called optical drives, such as DVD player, CD player, Blu-ray, whatever, all these optical drives pick up signal using a beam of laser. Medical devices, for example, excimer laser, which is being used to correct vision, laser vision correction for nearsightedness, farsightedness. Okay, we also use laser to perform surgery, other forms of surgeries, to stop bleeding and so on. Military applications, the typical laser that we use as a laser pointer, the beam is very concentrated, even though it doesn't put a lot of power out of it. It's so concentrated, it's still very bright, but it's only like of the order of milliwatts, 10 to the negative 3 watts. The military grade laser, the CO2 laser used in the laser cannon, can get you energy like 100 kilowatts. Okay, imagine a laser pointer pointing at you is already very, very intense, but that's a milliwatt, 10 to the negative 3 watt. This is 10 to the positive 6 watts. It can actually destroy things for military purposes. Of course, also laser-guided bombs. Here we don't use laser to destroy things, but we use laser to guide the bombs and so on. A lot of military applications, and also interestingly in energy research as well. In the National Ignition Facility inside the Lawrence Level 1 laboratory, we use a multi-beam system of laser to focus on on fusion material to create fusion. And it's a pulse laser which only exists, the beam only exists for a very small fraction of a second. But during that small fraction of a second, the energy output for all these laser beams is 700 trillion watts, 7 times 10 to the 14 watts. You compare that with the electrical energy consumption of the entire world over a year. This is the average value of the electrical consumption of the entire world over a year. It's only about 2 trillion watts. Here is 700 trillion watts. So we have achieved laser with incredibly high amount of energy. And this is only a very short list of the application of laser. There are many, many more applications. So we saw an overview of atomic physics in this chapter. Starting from the next chapter, we're going to expand beyond a single atom. We're going to see how atoms can bond together, sort of, to form molecules, and how molecules, or a whole bunch of atoms, can tie together to form solids. That is what we see in the next chapter.